All right, our first speaker this afternoon is Leia Shen, who comes to us from Harvey College. Leia's been working this summer with Josh, and she'll tell us about their project together, Lithium as a signpost for compact object binary candidates.
Thank you, Glenn, for the introduction, and thank you guys for being here. So first of all, let's start with some background of my study. Firstly, why do we care about compact objects, that is black holes or neutron stars? It's because they're important for us to understand the outcome of supernovae explosions and massive star evolution. Secondly, why use lithium as a signpost for finding these candidates? It's because lithium enhancement is often empirically found in many compact object binaries spectra, and that's the reason why we are using it as a signpost. Our work is motivated by the detection of Gaia NS1 by a mentor and Higgs collaborator, which contain its companion as one of the most massive neutron stars. And it's also showing a lithium enhancement as shown in the plot beside when comparing to a reference star. So we are using this target as a reference for our study. So for our goal, we want to search for compact object binaries in the LAMOS medium resolution survey, with firstly a similar properties as Gaia NS1, and secondly a lithium enhancement in its spectrum. For LAMOS, it's the abbreviation of Large Star Area Multi-Object Spectroscopy Telescope. For the first step of our research, we want to select those stars with similar properties as Gaia NS1. So firstly, we want it to be a main sequence star. That means its surface gravity should have a log G greater than 4. So we select all these stars from the most medium resolution survey. We also want the star to be metal poor. So we restrict the iron content of the star to be less than 1/10 of the solar one. To make this metallicity reasonable, we want to restrict the temperature range to be between 4,000 K and 7,000 K. So applying these three requirements, we select 6,109 stars from the medium resolution survey of LAMOS. Then, having this initial sample, we want to further measure the lithium abundance of these stars by fitting a Gaussian model onto a lithium absorption region. And then calculate the equivalent width by taking a rectangle with area equivalent to the area under the absorption region and divided it by the continuum level, that is 1 for the case of normalized flux. And then we derive the equivalent width of this star's lithium absorption region. And then we plot the lithium equivalence width distribution and fit a Gaussian model distribution to it. And using this two distribution, we set the threshold of equivalence width to be greater than 0.082 angstrom as our threshold for the star to be considered as lithium abundant. We set this threshold by taking the point where the data distribution becomes larger than the Gaussian distribution. And by setting this threshold, we select 27 stars. To ensure that these stars also have a good data quality for us to analyze, we also restrict that the star should have a spectra to have signal-to-noise ratio greater than 10 and no spectral artifact like this, where the normalized flux suddenly decreased to 0 around the lithium absorption region. This may interfere with our lithium absorption measurement, so we omit the star with this kind of spectrum. By taking the threshold of equivalent width and these two requirements, we select 21 stars for further study. Then we want to test whether these stars are in a binary system or not. So we take the first measure of taking the chi-square test for radial velocities to test for the likelihood of binarity. So for a star in a binary system, it will have a variation in radial velocities as shown in the animation, since it's gravitationally interacting with its companion. For the radial velocities, we take the data measured from the LAMOS medium resolution survey and Gaia data release 3. We then calculate the p-value of the chi-square test and set the threshold to be less than 0.05, which corresponds to less than 5% probability of obtaining the collected data with no actual variation in radial velocities. So by setting this threshold, we take 7 stars that have a p-value less than 0.05, therefore have a significant variation in radial velocities, indicating a binarity. Then we take the second measure, which is testing whether the star is wobbling or not, by looking at the Gaia renormalized unit weight arrow, which is abbreviated to RUWE. In the physics understanding, it's the extent of the photocenter of the star is wobbling. And in mathematical understanding, it's a square root of the reduced chi-square that is measuring the certainty of the star's position. To set the threshold of RUWE for binarity, we take account both the Gaia early data release 3 recommended value, which is 1.25, and we also take account of the minimum threshold for binarity over the sky map, which is 1.15, as shown in the figure beside. So by averaging these two values, we set the threshold for binarity of RUWE to be greater than 1.2. So by taking the RUWE threshold together with the p-value threshold, we found 4 out of 7 stars with low p-value and RUWE greater than 1.2. And their properties is listed in this table marked blue. So with these 4 final candidates, we look back to their Lamothe spectra to see whether they are satisfying our criteria. So by purely looking at the spectra, we can see that they are all showing a strong lithium absorption. However, there's one spectra that seems very problematic, as there are other absorption lines around the lithium absorption region. So instead of being a metal poor star that we want to look for, we suspect that it can be metal rich. To test whether that's a false target or not, we look back to the median resolution survey of the star, and we find that except of the first observation, all the other observations is showing a metallicity higher than our threshold and a surface gravity lower than our threshold. So instead of being a metal poor main sequence star that we are trying to find, it's actually a metal rich giant. And the reason we are including this false target into our initial sample is made caused by the first detection from the false detection from the most. And Gaia observation also supports the claim that it's a giant by having the log G to be 1.84. To further study the remaining 3 final candidates, like whether they are in a binary system with compact object or not, we further looking into their Lie curves by TESS, which is an abbreviation of Transiting Exoplanet Satellite Survey. We first take the original Lie curve and plot the periodogram of it to find the most likely period of it, and fit the Lie curve using that period to derive the folded Lie curve to see whether there's a pattern in it. So by searching the Lie curves, we found that 1 out of 3 candidates is showing an eclipsing binarity. And we measure the period of these candidates by taking the difference between 2 eclipses. However, for other two candidates, we are not finding any pattern in both their original Lie curve and folded Lie curve. However, we are not omitting these from our further discussion. It's because it may cause by TESS observation time is shorter or comparable to the period of the star, so we cannot see any variation in it. So for future plans, we want to further study the properties of the 3 final candidates through obtain more radial velocity measurements and also fit it with Phoebe, which is a Lie curve fitting software where, as shown beside, after the fit, we can get an estimation of the mass of the companion that can help us understand whether that's a compact object or not. We also want to apply the pipeline developed in this research to other surveys, including but not limited to Lamothe low resolution survey, SDSS survey, and Gaia ESO survey, etc. So for some takeaways and conclusion of this study, we found 21 stars with high lithium equivalence width from the 6,109 Gaia NS1-like stars from Lamothe median resolution survey. And we narrowed down 3 out of 21 stars with high likelihood of in-binarity. And we also found 1 star out of these 3 stars is showing an eclipsing binarity from examining their Lie curves. And our future plan, including to further study these 3 candidates by obtaining more radial velocity fitting with Phoebe and applying pipelines to other surveys. Thank you, guys.
Great, thank you. Questions for Leia? Johanna?
Thank you for your presentation. I was wondering, for the test data, how long do you know if those stars are going to be revisited in future observations of the past?
Actually, I'm not really sure about it. Yeah.
Any other question? Autumn?
Yeah, I have a question about the future or other spectroscopic data sets you're planning to apply this method. So do you envision any changes to the pipeline needed depending on the resolution or specific range that these other surveys are covering, or do you think it's going to pretty much be the same method?
I think for some of the survey, like the most low resolution survey, we may want to improve our Gaussian fit model because for low resolution survey, there's not lots of data point on it, so it may not fit as well as like the medium resolution survey does. So we may want to improve onto that, and also we want to improve on the initial sample selection procedure to ensure like those false detection like will be reduced.
Question.
I think we have time for one more. Yeah.
Okay, so CL would like to unmute and ask a question, so go ahead.
Okay, it's me, Casey.
Okay.
Sorry. Okay. Nice to talk. I was just curious, because you talked a little bit about how there's like those spectral artifacts and like some misclassifications from Lamos. Do you worry that this could have happened the other way around? By which I mean, maybe in your initial selection sample, you might have excluded interesting objects because they were misclassified?
You mean like because there's some spectral artifacts in the spectrum, so I may misclassify them from my initial sample selection?
Or say like the log G was actually like 4, but it was reported as 2 or something, like kind of the inverse of what you had, like, and then it wouldn't have made it through your selection to be followed up?
Yeah, that's why I mentioned like we want to improve on our initial selection procedure to ensure there's like no false positive or to ensure there are no other interesting targets excluded from the like selection. So that's one aspect we want to improve on.
I see. Okay, thanks.
Casey, and let's thank Leia again.